Hello and welcome back to the PyTorch tutorial series. In this video, we'll implement a full neural network training loop in PyTorch. We use the Fashion MNIST dataset, the same dataset we used in the previous video, and we even use the same neural network architecture as well. So the big addition here is that we implement a full training loop which includes the following steps. Step number 1, compute the prediction error, that is, doing a forward pass through the network and computing the loss or the difference between the predicted value and the ground truth. Step number 2, backpropagate the prediction error to adjust the model's parameters, that's the weights. Step number 3, update the model's parameters using the optimizer. This changes the model's weights in the direction that reduces the loss. Step number 4, repeat until the model is trained. An epoch, sometimes you hear it pronounced as an epic, it's one pass through the entire training dataset, which includes the forward pass, the loss computation, the backward pass, and the parameter update. We'll also compute the model's accuracy on the test dataset at the end of each epoch. This is called the validation step, and it's a good way to check if the model is overfitting the training data. This image is adapted from the book Deep Learning with PyTorch by Ali Stevens and Luca Antiga, and I just animated it to walk you through the steps of how a neural network is trained. So to summarize, the training data is fed into the neural network, and the neural network makes a prediction. Now this prediction is then compared to the ground truth, and the difference between the prediction and the ground truth, that's called the loss. The loss is then used to adjust the model's parameters, and the model's parameters, or the weights, they will then be updated. And this process is repeated until the model is trained. The model is then tested on a set of test data, unseen data, and the model's accuracy is then computed on that. Now, if you're new to deep learning, I recommend watching the backpropagation and gradient descent explanation video before watching this video. I created that video to explain it to you, just like I would to a 5 years old, so you could get an intuition for how all of this works. And when you're ready, let's get into the code and let's code it up. So let's start by creating our new file. I'm just going to click complete.py. So this is going to be an end-to-end complete example, complete implementation of neural network, bringing in all the knowledge that we have from the previous videos in the series. All right, so the first thing we want to do is to sort out our import. So let's do that. Most of this shouldn't be unfamiliar to you because we use the same imports. If you look at the kind of examples that we covered in the previous videos in the series, as long as you're following along the series, then none of this should be new to you. We would want to visualize that, don't we? So we want to just bring in TorchViz as well at the moment. And this is for us to visualize it. So when it comes to training a neural network, I like to put all of my hyperparameters all the way up at the top of the file. So just right after my imports, I like to put in my hyperparameters. What are hyperparameters? Hyperparameters are just adjustable parameters that let you control the model optimization process. So different hyperparameter values impact model training and maybe even impact your convergence rates. And this value may need to be adjusted to achieve optimal model training. So at a bare minimum, when we set up a neural network, when you create a deep learning model, we will need the batch size, the learning rate, and the epochs. We talk about a lot of this stuff. Again, if you have followed along this series, then none of this should be very new to you. So I'm going to create my batch size. For my hyperparameters, some people like to keep it lowercase. I like to put them in uppercase just to tell myself that they are kind of like adjustable parameters that I want to control, and I can change them. This is going to be 0.001, so I can write it that way. I can also use the scientific notation, and I can set this. For now, I'm going to set it to 2 because we're going to do this training back and forth, and I want to make sure that by not having too much epochs or epic, I can at least make sure that my code works, and I can adjust this. I can increase this value, so I can increase this to something reasonable. All right, so just write something there to tell myself that, hey, I want to increase that to something reasonable. You know what else I like to do? I like to set up my device as well. I like to say that if I have CUDA available on my machine, go ahead and use CUDA. If I don't have that, just use CPU. So let's also go ahead and do that. Say if torch.CUDA is available. We've done this countless times over the series, so nothing new here. So if it's not available, just use CPU. And just give myself a reminder of what am I using. So I like to say print, and I want to say print using device, right? Okay, now to start training a neural network, we need, at a bare minimum, we need 4 things, right? The first thing we need, let's put up the comments here. We said we need, so the first thing I need is the data. So I'm going to say the data. I need a model because that's what we're going to train it with. So that's our neural network model. Okay, this is a neural network model. And then we need a loss function. And then finally we need an optimizer. So let's put that in. So starting from the data, how do we get the data? This is something very similar. We've done that before. You could even just go ahead and look at your past, the code that you've written in the past exercises and just copy them. And at this point of the series, it's probably too trivial to go ahead and explain each one line by line. So I'm just going to write out real quick. Training, data. And I'm going to just say data sets, where is data sets from? That's all the way up here. So Torch Vision import datasets, and notice that there are a ton of datasets that was brought in. I can use any one of them, right? But we're going to use the Fashion MNIST. So I'm going to say Fashion MNIST. This is going to say look into the data folder. This is the data folder in my directory. This is it. I name it data, so I want to put in data in here. I want to take the train portion of this data. Want to download them if they don't exist. And then I want to make sure that all of that images are going to be converted to tensor. So I don't want them in NumPy. I don't want them in PL in the Python imaging library format. I actually want them in tensor format. All right. Test data is about the same, except I'm not going to say train equals to true. I'm going to say train equals to false, because that will make sure that I get the test portion of the data. So this is going to be false, but everything else is the same. Remember, we have the data loader, so it's time to turn them into batches, turn them into mini batches. So we're going to say train data loader. And we want to call data loader, and we just have to pass our training data. Want to say batch size. Okay, this is where you can hard code that value, but since we already defined that up here, it's 64. We want to just call batch size. So we're going to say batch size, and do the same thing for test data. And instead of training data, what do you have? You have test data. That's what we name it here. So let's make sure we name this test data. You can put a quick save here. So this is the first few lines of code. We've done the first part, we've done the data. So this is checked. Maybe let's put this here instead. Now, if you want to, you could go ahead and just maybe quickly print out the shape of the data. You want to print out the, say you want to print out only the first one, right? So how would you do that? You can say for, you can say XY, but because X is going to be somewhat like a matrix, so I want to put them in capital X, just to be more explicit, just remind myself. And I want to say iterate over the test data, and you can iterate over the train data. It's the same thing here. We're really just checking the shape, so it doesn't matter if you're doing the train on test, but you could just do a print, and you can just tell yourself like, okay, the shape of X. Optionally, let's also look at the D type. So we want to see like, okay, what are we trying to predict here? Now, ideally, you want to have this being a tensor of the type of integer, because you're predicting the class of 0, 1, 2, 3, 4, 5, 6 all the way to 9, because there are altogether 10 different classes in our Fashion MNIST dataset, right? So there are altogether 10 classes. You want to check that this is either that, or it could be maybe a string or something. You want to make sure that just do a D type and give yourself some sanity check. This will run for each one of the items in the iterable, so you don't really want that. You only want to print it one time, and then you want to just break. So it doesn't go ahead and just print out all this redundant information to you. Just say break after the first one. So let's count this as done. Now the second one is a model. The model is something we've done in the previous videos as well in this playlist. So it's also nothing very different from that. Remember, we have the NN that we imported, so from Torch import NN. So turns out we can create our own class of a neural network, and then we can just subclass from that. So let's go ahead and do that. Class neural network, subclass from NN module. You need to initialize. You said when it first create this, when you create an instance of neural network, what should happen? You first want to take the images. Let's go ahead and just pass this. Before we do anything further, let's go and do a quick sanity check. Let's do a quick sanity check, make sure everything is working. So let's say activate my virtual environment, python.py, that's the name of our script. And so we see 64, 1, 28, 28. So that's the size of the mini batch. That's correct. We verified that 64 here. And this is the channel. There's only one color, so it's only RGB. No, there's only one color, grayscale. If you have RGB, you probably see 3 here, right? But here this is only one color, so it's only one channel. And then 28, 28, that's the width and the height. If it helps, you could just maybe put it here. You can say this is the number of training examples, the channel, the height, the width. And if you're asking why is it height before width, no, why not width and height? Well, because in the computer vision field itself, when you're working with like OpenCV or NumPy, generally speaking, we always look at the rows first. And basically, if you count the rows and then the columns later, in the field of numerical computing, we always look at the row first. So just like how you use pandas, the first index is always going to be the row first and then the column. So the number of rows would be the height, right? Because many rows of an image would be height of the image. Columns would pertain to the width of the image. So that's why height and then width. But now you have a problem, because you don't want to have 28, 28, because that's not how your neural network is going to set up. You want to have it as one big array of one continuous, one contiguous array, so touching each other, one continuous or contiguous array of 784, which is 28 times 28. So the first thing we want to do is to first flatten that. So instead of a pass, we're going to add a comment here. We say that we want to convert the 2828 pixel. We want to convert that 2828 2D image or pixel image into a contiguous array of 784 pixel values. So you just want one array containing all of that. You don't want to have to, because you want to flow this 784 into the neural network, flow it through the neural network. So you want one contiguous array now into the input neuron of your neural network. So how would you flatten all of that? Well, turns out you could use nn.flatten. So you can create an instance of that first. So I'm going to create an instance of, I'm going to say, create a method on this class called flatten, and that I can call later. So I'm not calling it yet. So I need to create a forward, and it would take self, it would take x, and then you would take x and you say self.flatten, too many t there, x. So every NN module subclass will implement this operation on the input data. So it would take the input data and then it will run through this forward method. Generally speaking, you don't actually implement, you don't call this forward function directly. Instead, what you do is you just say model neural network, and then in your train loop, later when you run through the loop of your epoch or the epic, each time you call the neural model and you try to run the data through your neural network, it's gonna automatically call the forward for you. So you don't, generally speaking, you don't actually call it directly. Okay, let's go ahead and complete our architecture here. So we have this. Now, the last time we used a linear value stack, we're gonna use the same architecture. So just to keep it tidy, we're gonna use the same one. We're not gonna introduce any new concepts here. We're gonna again use the sequential container, just create a sequential container within it. Now everything here would be sequential, so they're gonna follow one after another, right? There is a some sort of ordering here. So the first one, the input layer, because we have 784, now you can put 784 here, so that's the amount of input neurons you have, or you can just put 2828. If you don't want to do the math yourself, you can say 2828. And then what about the hidden layer? How many neurons do you want? Now the last time, if I recall correctly, in the last video, we said 512. So we're gonna stick to that, okay? Then we're gonna have nn.linear. Now this, we have to take whatever it is from here. So 512, you want to have 512 here. And then you can finally have an output. Now the output is not up to you anymore. This is the output of the hidden layer, so you want to carry that forward. But then the output of this is the number of classes, right? So in this case, we're predicting the MNIST dataset. So there are altogether 10 different classes, right? There's the shirt, the t-shirt, blouse, the dress, the jeans, the head, the bag, all kind of things. But they're altogether 10 classes. So want to put 10 classes in here. We want to have an activation function on each of the neuron. So here we're just going to use the value. We talk about why we use the value over the sigmoid. We discussed about that. So in the earlier videos, we go through how to think about this, how to architect that. And if you want a more detailed explanation of what this is doing, then I would point you to that video where we really cover the architecture. This video is really just copying code from that video and pasting back in here. All right, so there's really nothing fancy in here. And I don't want to be repetitive where I repeat the same stuff over and over again. Just make sure that you spell value correctly. Just like when we defined this method, we didn't really call it, we only defined that method. So we want to also call it. So how do we call it? We said you can, I'm going to call logits. So that's the logistic regressions. And I want to say take that and then call, what do I name it? I name it linear value stack, so I'm going to call it here. If you name it something else, then you want to change this accordingly, right? So this will take x, and then it will run it over this, and then the output of that will be logits. And then finally, you could just return that. I want to do one more thing before I move any further, is that I want to say that if I have the GPU for it, then move it to GPU. So I want to say x equals to x.to, move it to device. Where is device from? It's right up here. So that's CUDA if it's available, if not CPU. And so simple enough, let's also do it for to device. If you want to just take a quick look at the model, check that everything runs as expected, you could just go ahead and just print it out. So that concludes the second part of the model. So let's go ahead, put an X to it, and then if you want to, you could also just run it again. And good thing we run it because we see that there's an error, we can quickly fix it. It says model equals to neural network to device. And that's in here, we need to inherit the nn.module, so that to inherit that, we say super, and then we want to inherit what method of that? We want to inherit the init method of that. So it needs to go ahead and inherit this, initialize all of that first, and then this is where you override stuff, but you want to inherit that first. Okay, now it seems like everything is working. There is the type is there, the shape is there, the type is still correct, integer, that's good because we want it to be integer, altogether 10 classes. Then we flatten stuff, flatten everything from 2020 to 784, and then we pass them into the sequential network, and then within the sequential network, the first layer, 784 neurons, output 512 with the bias, and then 512 output 512, and then 512 output 10. Each one of them, the activation gate would be value. Okay, great progress. Now let's see what do we need. We need a loss function. Now a loss function is the function that the models try to minimize during training. If you learn about neural network and you watch the earlier video about backpropagation and about gradient descent, then you know what a loss function is, right? It's the function that the model tries to minimize during training, right? So it gives you a sense of like how bad is your model, how much of a good fit or how bad of a fit your model is towards your data. The outcome of that is that you get a better model over time. So what is a common model for classification problems? Today we talk about the cross-entropy. So I'm going to use the cross-entropy. And it's also in the NN itself. So from Torch import neural network, it also implements it from there. So I'm going to just go ahead and say loss Fn, loss function would just be cross-entropy. Now to give you a sense of what cross-entropy function is, let me get into my terminal. I'm going to say Python. I'm going to go ahead and just import Torch. Let me just create an X, and I want to create a Torch, create a random tensor, and the shape would be 3, 5, track the gradients. I want to do the same for Y, so I'm going to create 2 tensors. So notice that these are all random tensors. So if I show you X, this is Y. They are very different because this is 0.649, this is 0.3756. They are not the same. So if I were to use the loss function, so let's go ahead and bring in the loss function. From Torch import NN, then what do? We say loss function NN.cross-entropy. So I'm just going to be lazy here and just copy that, paste it in here. Now if I say loss function, and I put X and X, so meaning X against itself, I should expect a very, very low value because the loss should be very minimal because they are the same thing. I'm comparing the same, right? X against itself. So I should expect a very small value. Let me run that. So it's a -4 value. So that's great. That's very, very small. But if I compare the loss between X and Y because they are different, right? So let me see, run X and Y. You see that the value is larger than the X value. Now, the way you think about this is, suppose that Y is the ground truth. This is the actual values, and X is not the ground truth. X is your prediction output, right? This is what you predicted the values to be. This is the ground truth. What do you want? You want them to come to very close values. So you want to predict values that are very similar to the ground truth, to the actual labels. If they are in fact the same, you will get a very low value. If they are not the same, you get a much higher value. In this case, it's a double of the value of this. Let's take a quick break into RStudio and take a look at what the cross-entropy error is. Again, I'm using materials from the Academy. So if you follow my work, I run a few things, but one of the things that I do is I teach at this bootcamp called Algorithmic Data Science School. I started the company in 2016, so it's been around for about 6 years now. This is the materials from that. Okay, so this is the code that implements the cross-entropy error. So this is how it looks like, right? This is the cross-entropy error. You have the Y, and then you have the O. The O is the output, the Y is the ground truth. I'm going to show you how that looks like in code. If I implement this into code, you see that they're pretty much the same thing. You see this is Y minus Y, 1 minus Y. This is also the 1 minus Y. And then you see the multiplication between Y and the log, right? This is the Y, this is the log of the output. This is the same thing, the Y and the log of the output. So this is the log and then the 1 minus output. This is log 1 minus output. So this is kind of the same thing in here. I just implemented that into our code. And then what we're gonna do is we're gonna run this code. So let's run that. So I have the function. The function takes 2 parameters, X and Y. So I'm gonna show you a few examples here. So I have run the CE manual. Let's go ahead and run 0.1 and 0.12. So what you realize is that because this comes close, 0.1 and 0.12 come close to each other. Let's say this is your predicted output. This is the ground truth. You should expect a much lower value. But as this gets to 0.1 to 0.2, this is a much bigger difference. This is a much bigger error. So your CE manual is going to be larger, right? And then 0.1, 0.3, this is also larger. So again, your CE manual is going to be larger. So your cross entropy is going to get larger the further away these two values are. If you want to just go ahead and try that again, I'm going to go with a smaller, even smaller values. Let's say 101. You see that now the values is even lower. If the values are great, let's change this to 0.3 to 0.4, for example. See now the values get a lot larger, right? So that is, in a nutshell, that's a cross-entropy loss function. You want the values to come close to each other. When they're close to each other, you get a bit of a loss, but the loss is not great compared to if the values start to deviate from each other. In R itself, when you write the manual neural network function, you look the code looks very similar. So x, y, epochs, learning rate, and then you see that I'm gonna do my mat mul. I'm gonna update that, gonna find the difference, and then assign that back, and then use that to update the weights. So beta would then be updated because this is the beta, and it would be assigned a new value based on the delta. And the delta is not gonna just apply wholesale. You're gonna actually account for the learning rate. So in this case, I'm gonna say whatever the derivative is, whatever the delta is, adjust that by a small amount. So you want to take a small step towards that direction. Finally, I'm gonna just use C manual, which I write up there to run that. So that's what we're gonna do in Python as well. So let's close that out. So going back to Visual Studio Code, we have our loss function. That's kind of, it's a very quick explanation of what that is. But we did have that crossed out. So we have a loss function. And now we need an optimizer. This is the optimization algorithm. And if you watch the earlier videos about gradient descent and backpropagation, then this should come as no surprise. We are going to use the gradient descent. We're going to use the stochastic gradient descent. So I'm also going to create the optimizer. And I'm going to say torch. Now in torch, there is this optimizer called optim. I'm going to bring that in. And within that, there are a few that are implemented for you. Sprouse, Adam. So there's the Adam grade, stochastic gradient descent. There's a few others here. There's altogether 6 choices here. And we're going to use the SGD, stochastic gradient descent. We're not going to talk about the rest in this video, but in future videos, I may go into some of the differences and stuff. Off the back of the last video, we spoke about gradient descent. I want to just stick to gradient descent, all right? But all of them use the same principles of what you learn when it comes to backpropagation and gradient descent. If gradient descent is still the backbone, regardless of which choice you have, and you kind of need to learn gradient descent, even if you choose in the end not to use the stochastic gradient descent and go with Adam grad, for example, all right? Now, you will want to pass in the model parameters, and the way we do that is usually just model.parameters, and this will take all the parameters in the model, and then you want to pass in a few other things. So one thing you want to pass in is the learning rate. If you look at the learning rate, it says pass in a float value. So you can say LR and then pass in a value like 0.005, just like what we see in our studio. But since we set that up as the hyperparameter right up here, so I'm going to copy that and I'm going to paste it right in here. If you want to be a bit more fancy, if you learn about neural networks or have some experience with deep learning, maybe you have used Keras or TensorFlow in the past, then you may have learned about momentum. You can also set a momentum here. So I'm going to set momentum to be 0.95. Momentum helps accelerate the gradient vectors in the right direction. It pushes the gradient vectors in the right direction, and it can lead to faster converging. So momentum is actually a relatively easy concept to grasp once you see the formula. So this is the formula. When you look at this is the V is your sequence, right? And this is B, the beta. Now the beta is value that you got to pick, and for example, the author here says that he picks the value of beta equals to 0.9, and generally you want a value of 0.9 and maybe above, right? It is a good value and most often used in stochastic gradient descent with momentum. Intuitively, you can think of beta as follows. We're approximately averaging over loss of 1 divided by 1 minus beta points of sequence. Now, what does it mean? So if I pick a value of 0.9, now this is my original sequence, 0.9 times that sequence shifted by a value of 1 behind. So you're taking that and then you're adjusting the value just so slightly. And why is it just so slightly? Because you pick a beta value of 0.9. So you're just moving that a little bit. So instead of a 10, you get a 9. Instead of 100, you get a 90. All right? Just multiply that by 0.9. And then this is 1 minus the 0.9. So this is 0.1 multiplied by the S of t. So this is the sort of the conclusion there. Instead of having data with a lot of noise, we got much smoother line, which is closer to the original function than the data that we had. Exponentially weighted average defines a new sequence, V, instead of using the S, right? So this is how it looks like. And by changing different levels of the beta, so instead of 0.9, if you have 0.98, this is even smoother than the blue line, which is 0.9, which is even smoother than the 0.5. And this kind of makes sense because this is not a complex function at all. It's very easy to intuit about. If you learn anything about forecasting, and you may have come across like exponential smoothing, this is very similar to that idea, except exponential smoothing would assign a value into prior time steps, but yours is just moving everything by 1 and then adjusting that. So a value closer to 1 indicates that the most recent value influenced the forecast, whereas value closer to 0. So it's not a complicated concept at all. Now let's go back to our code. So sort of the beauty is that instead of having you to do all of that, manually writing the code for that, it actually just provides for you already, and you just have to bring them in. They're ready made for you, all right? So you have the loss function and you have the optimizer with a momentum 0.95. We explained all of that. So we now have all of those 1, 2, 3, 4. If you want to at this point, you could put a save here and then you could just try to run everything. So Python and put a complete py. Don't forget to activate your virtual environment. So I'm gonna have to do that, run it again. And okay, everything is working now. Now the last part is to define the loop. So this is not used yet. The epochs is not used. We already used the batch size, the learning rate, but the epoch or the epic is not used yet. So let's go ahead and use our loop to now do the training. And you can see something like for t in range instead of putting 2, you don't want to hardcode that value. You want to actually call the variable there up there. So epochs or epic. And here you want to train our model with an optimization loop. And notice that each iteration of the loop is an epoch. Maybe you also want to say that each epoch consists of 2 parts, the train and test loop. So let's go ahead and basically run a do training. You can say do training. Now we don't have do training yet, so let's go ahead. Instead of calling it do training, let's call it something more sensible. Let's call it the train loop. Okay. And let's go ahead and define the train loop. While we're there, let's just also define the test loop. So say test loop. And with the train and test loop, we're going back to the original mental model at the beginning of this video, right? We spoke about the training data, how we pass that into the neural network in a forward pass. In the forward pass, the neural network will make a prediction. The prediction is then compared to the ground truth, and the difference between the prediction and the ground truth is called the loss. What do we do with the loss? We take that and we backpropagate the loss in order to adjust the model's parameters. Then the model's parameters will be updated, and this process is then repeated until the model is trained, and it's repeated in how many cycles that's defined in the epochs. So let's start from the train loop, right? So what do we need in order to run this train loop successfully? So we want to have the data loader and we want to have the model. At the beginning here, we have the data, the model, loss function, and optimizer. So we want to bring all of this in there. You can take all of this, just copy them down just so you can have a very easy reference. Just gonna put them in here. I'm going to delete that right when we're done. But you want a data, and so the data is in your data loader, so we might as well just put a data loader in here. And then we need a model. That's the second item we need. Then we need a loss function. Then we need an optimizer. So this is basically the 1, 2, 3, 4 that we need. And you want to remember what you name your data loader. In this case here, it's the train data loader and the test data loader. So you either want to just copy that and paste it in here, and you want to paste the same thing here, but you want to change this to test. Now, what about model? What do you name your model? So let's take a look here. We name it the model neural network to device. So that's model. So we want to pass that in as well, and we're gonna do the same thing for test. So this also have to be set up to take at least data loader and the model. Now in the test loop, we want to calculate the loss function because that gives us a sense of the accuracy, but we do not need an optimizer because we're only just going to test and see, okay, giving an exam to the model, the neural network model, and said, what is the score on this? So using the loss function, we should be able to calculate the accuracy. We do not need an optimizer because we're no longer doing any kind of training in here, right? Since we have the loss function in here, what do we name it? We name it loss function. So we just might as well just pass that in. So pass in loss function, pass in loss function. And that is done for test loop. We need the last one, which is the optimizer. What do we name it? We name it optimizer. So we want to also pass in the optimizer. If you want to give yourself some comments to help yourself, you can write something like trying to iterate over training data, and try converging to optimal parameters. And the test loop itself is, the goal is very simple. The goal is to iterate over test data and check accuracy. And maybe to see if the model performance is improving. So it's going to run 1 time and then run 2 times, because run 0, 1, 1. Why? Because epochs is 2 right now. We define that as 2. So it's going to run 2 times. The first time it's going to go through the data loader, run through all of that, and then do a test, run through all of that. And then it's going to repeat the process. And each time it's doing that, we want to actually get them to print out the result. So we know that, hey, at least it's improving in terms of performance. Now, what do we do with the data loader? We need to enumerate that. So instead of pass, let's actually write this out. So we say for, and there are 2 things. When you enumerate over data loader, it returns a tuple of 2. The first one, we can just call it batch. So the second thing that it returns is the x and y when you enumerate over data loader. So I want to say enumerate data loader. And this behavior is given to you from this, right? So you say data loader, it's going to return this train data loader, and then this train data loader itself, if you enumerate over that, that's the index, and then each one of them, it would have a tuple of 2. This is the ground truth, and this is the training data. This is the big 784 array of pixel values. All right. Now, because we're doing all of this in CUDA, if you have a compatible device to support it, so we want to also move x and y CUDA if you can, right? If it's possible. So you say x, and if not, it would just use the CPU. So no big deal. I want to say to device. Want to put y. want to say y to device. And now we do our backpropagation. So now we say this is where we do our backpropagation. Now, before we do a backpropagation, you can actually separate this into like forward pass and backward pass. You can say something like forward, and then you can say backward pass if you want to just maybe name it like that. Okay. Now, in the forward pass, you want to basically say spread equals to model x. I believe we've seen this before, and that we'll just call the forward for you, right? Once you compute the forward, what happens? You want to basically calculate the loss. You want to compute the prediction and the loss. Let's actually put something like this. This is the forward plus backward plus. So this is the forward backward optimized combo. Not combi, but combo. I'm not sure that's the plural of combo is plural combi. But we now compute the loss because you want to see how away are you from the truth, how inaccurate you are. And this is how we do it, just like how we see it earlier when I open up terminal and I just call a loss function and I put two values in there. You see that the lower the better, right? Lower means that the pred and the y come very similar to each other, come very close. Now, if the value is very huge after we pass into this function, it means that they are very far away from each other. Then once you have the loss, you want to backpropagate that. You want to go into the backward pass, and the way you do that is you call loss.backward. Very simple. But that's not updating anything yet. To update it, to actually use the optimize, to actually update the weights, you want to say optimizer step. And that will actually update the weights for you. Now, there is a small details here that I think I should mention. You can put it anywhere before the loss.backward, but you need to set your optimizer to 0 grad. And let me explain what this is, alright? Now, 0 grad sets the gradient of all the optimized torch tensors to 0. This is because by default, gradients are accumulated in the buffer. So whenever the backward is called, every time there's a gradient, it's actually adding to the gradient. So it is accumulative. So what you want is to set this to 0 before you call backward. So you don't want to, you can pass this in here. If you want, you can take this and you can pass it in here. You can do it in here, but definitely not do it after loss of backward. So you want to set it to 0, set it to a clean state of 0, and then calculate the gradient and then do your backward pass so that the gradients are not accumulated every time you call loss of backward. So if you want to remind yourself what this is doing, this is kind of like setting the delta of W, which is your weight, and delta B, which is your biases, to 0. So that every time you call it, every time you run through this one, you start from a clean state again, and then you calculate gradient, and then you take a move again, and not accumulating it, right? That would be the wrong thing to do. At least not in the context of a neural network here, except if you're doing some sort of RNN, but that's a bit beyond the scope of this topic of what we want to cover today. And this is it. So every time it runs, it will go through all of this from top to bottom. But if you want to, you could actually say something like print the loss and say what is the loss function here, and you could basically have loss.item. But this will be quite spammy in terms of your terminal. So what we want to do is we want to maybe say something like do it for every 100. So at the increment of every 100, so 100 times 64, batch size like 6,400. So every 6,400 training images, add a comment here for every increment of 100. And here we have 64 batches. So we have 64 batches times 100. That's 6,400 samples. Print the loss. Just take a look at whether or not our neural network is doing better. Some of this stuff is getting a bit unyieldy, so I'm gonna maybe abstract that out, take this out, and move it up here maybe. So I'm gonna say size of this batch would be the data set, and then I'm just gonna replace this with size. In fact, you can do the same thing for each one of them, but I guess this is fine. You could save all of that. Before you even do the test loop, let's go ahead and just run it. Do not have that set. Okay, well, it doesn't have that set because we did not spell it properly. So let's name it properly again. So you see that the loss is actually starting to come down, right? 2.2, 2.1, 1.2, 0.8, and start to come down. That's good. That's what we want. But the precision is getting a bit unyieldy. They get too many of them. I actually want to maybe limit them. So a reasonable strategy is to sort of limit them to, let's say, 5 decimal points if you want to, right? And you can do that in Python, just putting 5 float precision. And size, you could also have some adjustment there and just say, oh, I don't want it to have. But in this case here, it's okay. But let's take a look really quickly. So I say that this is every 6,400 sample. So initially you have 0, and then 6,400 times 2, 12,800, 19,200, 25,600, and so it's incrementing at 6,400 samples. So at every 6,400 samples, you're gonna go ahead, reprint this loss. So you're actually gonna compute the loss anyway, but you're printing that out to show yourself whether the loss is actually coming down or not, right? Because if it's doing its thing, if optimizer is doing its thing, it should bring the gradients, it should nudge the gradients in the right direction, such that the loss should start to come down. The loss function should start to minimize, all right, start to converge. So that's great. This is doing its job. Now we can do the same thing for the test. I don't think there is a point in trying to move this in here. I think it should be outside. So let me bring that, because that's very handy. I'm gonna also pass that into the test loop. Now with the test, we're not gonna try to use optimizer anymore, because that is kind of the whole point of splitting the train and the test in the first place. If you're also gonna use optimizer on the test, then what's the point of splitting the train and the test, right? So you separate them so that you only train on the train data. You're not gonna look at the test data, you're not gonna cheat. But once you have a good enough model, you're gonna use the test to check an accuracy and see whether or not if your model has actually improved in performance. So if you want, you could also create some sort of helpful variables here. You can also say number of batches, and that's the length of the data loader. And then we want to initialize some sort of test, some sort of loss. So I want to say test loss, and let's also initialize correct. And we say 0 to 0, just initialize them. You could now follow this process of like for batch and then XY and then enumerate. We don't need this batch index, so we don't even need to call enumerate. We just have to go so for XY in data loader. So that's what we need to do. So let's go ahead and say for XY in data loader. Now I want to talk about one thing, is that if you were to do this, this will all work. But if you want to speed up your computation, you should set gradient tracking to be off when you don't need them. So what I mean by that is you have to use you can use a context manager, or you can just set up each one of the tensor, just set them to be no tracking manually. But this is a context manager that Torch provides for you, and so you should use that. Right? Now what does this do? This is a context manager that disables gradient tracking. So even if X and Y has gradient tracking set up, so when you see me, every time I show you some sort of demo, I will say Torch, and then I'll set the gradient tracking to be true to turn it on, right? Now, even if X and Y has gradient tracking to be true, as long as they're under this context manager, all of them will be set up to be false. So this will save you some memory, and will save you some sort of some computation power as well. You don't have to track the history, because you're not doing any kind of optimization anymore, right? So again, we're disabling gradient calculation because now we're only doing inference. We're not doing any kind of training. We're not doing any kind of optimization. We're not even doing any kind of backward propagation. We're only trying to make a forward call, trying to do a prediction, and then trying to calculate the loss. And that's it. We're not gonna backpropagate. So there's no point trying to store all the gradients if you're not gonna do anything with it. So even if you remove this, this will still work, but this will reduce memory consumption for computations that would otherwise have the required grad equal to true, right? So this turn it off even when you have X and Y set up to be requires gradient to be true. So you want to do very similar to what you did up there, which is the X and Y, move them to device. So let's copy that, move that in here. And again, very similar with the forward pass up there. The forward pass, you have the but instead of backward and optimize, you only have the forward pass. So you only need this and this. So I'm going to copy these two as well. So you're doing the forward pass, but you're not optimizing anything, just trying to do prediction, only for inference. So you can do the same here. You can just create the test loss. Instead of, I'm just going to give it a better name here instead of loss. I'm going to call it test loss. And test loss that is in here, we just add to that. So while it starts from 0, at each of these iteration, it's gonna take the loss function, it's gonna compute that loss, and it's gonna pass it back in here. So let's say there are 3 batches, and each one of them, let's say each one of them has 500 images. Let's say 300 images. Make the math easier to count, right? It says what is the test accuracy, or what is the test accuracy, or rather what is the test loss. It's the same thing here for the first 333. Then it do the second one for the second 333, and then it do the third one for the third 333. We start off by actually initializing the inaccuracy or the loss to 0. Then as we run through each one of them, we add to that. We said, okay, in 333 let's say we make 11 mistakes. So now we have 0 plus 11. Then we make 9 mistakes, and then we make, let's say, 14 mistakes. Or 15 mistakes. So now we have a total, we say 35 out of 1000 images. So after running through all the 1000 different test images, we make 35 error, right? 35 misclassification. And so you can now have a accuracy, and that's 3.5%, so that's 96.5% of accuracy. So this is what we're doing. We're taking the test loss, we start from 0, and every time we run through it, we just add to that. Now this is your prediction. Your prediction will look something like that. Let's say you have a class of 5. You have something like 0. So in total, this will sum up to 1, right? This is total probabilities. But what this is saying is that there is a 40% chance this is a class number 5. There is a 15% chance it's class number 3. 25% chance it's class number 2. 20% chance is a class number 1, and then there's 0% chance. Generally, you won't have a 0. You have something very small. But anyway, let's simplify the math here. So we're doing the same thing here. We want to say how many of them are correct. Let's go ahead and say correct. And want to do the same thing as what we did on the test loss. So we say that if you were to predict, so take the argmax in the first dimension, and if that is equal to the actual value of y, right? If this is true, then add 1 to the correct. So correct starts from 0, but if this is true, and this is how you check for that, right? You're saying that how many times did it agree with the ground truth? And the ground truth, the y itself, you get it from the data loader. So this is how much, this is how often you're correct. So from 0, it's gonna add and add and add. But we want to actually sum up how many correct do we have in total. So we need to convert this into some sort of a numeric format, either a float format, and then we can sum them up. So let's go ahead and do that. We say convert that to a type of float, and then we do a sum. Okay. Then we want to take the raw value out. We want to pull the value out. We just say item, just kind of like what we did up there. Whenever you call item, it just pull the value out into from a tensor into just a Python numeric, right? So we have an item, we just call it out, and that's kind of it actually. If you want to be fancy, you could also print a test accuracy out there. Let's do that as well. So let's say print. Now, if I want to pass this correct, this is not very useful if it's not percentages. So I want to correct for that by dividing the number of sides to give you a percentage. So I want to say take this and then equal to divide. Equal to correct divide by something. But I could do it faster by just saying divide equal and then just size. So size is up from here. Okay. So in total, if there are, so what it is doing is to take all of this 1000 and divide by the number of the total. So in this case, you're doing something like 35 divided by 1000, because 1000 being the size. So this is what we're doing exactly. Since you're doing that, you might as well also do the same thing for test loss, and you're also going to say number of batches. So you can also quantify the error that you make per batch. It's the number of batches. And with that, you can now treat this as a percentage, which is great. So it's 100 times correct. Remember how we said we want to a certain decimal point to a certain amount of precision? You can also do that. You can say like 0.1 f. Now you treat this whole thing as a percentage. Since this goes up to 5 decimal, let's also go up to 5 decimal here. So 5f. Let's save all of that. Let's quit out this one. Now the moment of truth, did we run it correctly? Python complete.py. Okay, so stepping by 6400. And then finally, the test error, the accuracy is 81%, and average loss, this is basically per batch, right? Each batch, this is how much, but the total accuracy is 81%. So this is kind of the total loss here. So the first batch, we have 11 mistakes. Second batch, we have 9 mistakes. The third batch, we have 15. We sum them all out. This is kind of what it's doing. It's taking all the test sample and it break down into mini batches, and then it gives you the sum of that as well. So now you have, in total, you make 19 out of 100. So for every 100 examples, you make 19 mistakes. And that's actually not too bad. Pay attention that in the test loop, you're not doing any kind of backprop. You're only doing an inference. You're kind of doing half of what you're doing in train, because you're only going to the forward, predicting that, and then calculating the error and paste it into your console. You're not actually passing any kind of backpropagation. You're not doing any kind of optimization there. Let's actually go ahead and add our visualization, because we did bring in our torchviz make dot. We did not use that yet. So I guess we don't need to print out all of the stuff, but we at least run the visualization, print it in the last, maybe here, print it here and say this is where we, on last loop of the training, of the train test cycle, produce. So we say if t equals to, how do we say take the last one? We say take the epochs. This is 2, so this is 2 minus 1. Go ahead and call make dot. This is something we learned in earlier videos in the series as well, so nothing fancy in here. Most of you should be able to get to this without any issue. You could optionally have it render. Call this a full complete example. Complete example. If you want to give it a format, go give it a format PNG. Now all of this is done. Once 1 and 2, because we have 2 cycles, we have 2 epochs. So once the both of them are done, we want to just print done. Okay. You can also be fancy and just say print done, and then with how many epochs? With how many epochs? But I don't think it's necessary, because it's pretty straightforward. It's not difficult here. The first time it runs, so this is a epoch, you set it as 2 at the beginning, so that's epoch equals to 2, that's here. So if you take a look at it, you would expect the test loop to run 2 times, because the first time it runs through 1 loop, 1 cycle, then the second one, so you would expect 2 different test error here. So let's take a look at the first test error. The test error, the first one is here. So this is the first time, the first cycle, and you have a test error, 77.8%, average loss of 0.644. Then the second one is when your loss goes down, which is good, and your accuracy goes up, which is also good. So you increase 81%. So now, to make sure all of this work, we could go ahead and improve the model, or rather the training, by improving the epochs. So let me just go and set this up, and I can remove this comment now. I would just set that up to something reasonable, like 10. And I'm going to run this, and hopefully I get better than 81%. And after 10 cycles, we now have a accuracy of 85.7% with a loss of 0.4. That's actually not too bad, right? That's not too bad. It's just for something that we coded up so quickly, in under an hour, we get this result. That's not bad at all. But what if we want to save ourselves some time in the future? We don't want to keep on training this. We could actually save the model, okay? So what we need to do is to provide a path, and let's go ahead and save the model. We say torch.save, and we say model.what? State dictionary. So this is going to save all the state. So basically the model is not something very magical. It's really just a bunch of weights and a bunch of biases. It's telling you that, okay, that is the state of the model, right? There is the weights and the biases. That's really what it is. It doesn't save anything. It doesn't save the images. It doesn't save anything except for just think of it as an ND array of the weights and the biases. And so give it a name. You can call it model. And if you save the model, actually let's run that. I'm also going to just copy this because I don't want to rerun this again because the video will be too long otherwise. So I'm going to say torch.save, run it, and what do you see? You see that a new model, model.pth, is created, and you can now use that model. You can load the model to make inferences. So how would you load the model? So I'm going to clear my screen now, and I'm going to show you. The first thing is to pretty much repeat the same thing as what you did up there. So remember, you have the model equals to neural network. So you could do the same thing. You can say model neural network. So create an instance of that. You can also load it into device, which is your CUDA or your CPU. But if you want to just keep it simple, you could just load it in there. And then the next thing, this is where the key is, right? So this is how you save the model. How do you load the model? You say model. Instead of actually passing, retraining it and assign the weights, you can just say load state dictionary. And so what this would do is to propagate look at the initialization of the neural networks and stuff. All of this, right, is going to pass that like a save game, almost like you play a game, you save the state of the game, and then you load it back into the game, right? Now, this is where you specify it. So you could put everything into one line of code, or you can separate them out, and you have to pass in the path. I name it model.pth, so I'm going to do it model.pth this way. Going to run it, and it says all keys match successfully, so that's cool because that's how you know that this architecture and the state that you're loading in there, it matches. Then you could just go ahead and say x, y, and you say something like test data, and hopefully we still call it test data. Test data. So let's just take the first one, right? Let's just take the first one. Let's keep it simple, just to show you that it works, right? So 0, 0, 0, 1, respectively x and y. Then we have the model. Now we need to put them into device because if we don't, it's not gonna run because the x and y are still on devices. So we're gonna say that. Okay, it's done that already, so that's the neural network. We see that the architecture is still the same. So move X also to device. Okay, now is when you wanna, if you just wanna do inference, you could wrap everything into with torch no grade. So you could do the same thing with context manager, but just to demonstrate, I'm gonna save this step for you. But if you wanna, if you're doing this for real, you wanna also add the with torch no grade, okay? So I'm just gonna go ahead and say pred, and predict what? Just exactly like this, right? So let's run that. So let's call pred. We're gonna just, because this is a list in the list, we just want to take that list. So we'll say pred 0, that's just gonna give you this. And by the way, I keep saying list, but this is really a tensor, right? So you say argmax, and again in this index, which one is the maximum? So this is tensor number 9. So this is number 9 is the biggest one. It's saying that this has the biggest probability of being the class number 9. Now let's actually compare that to our ground truth. Our ground truth is in y. So let's compare y. It's also 9, so this is 100% correct, like 100% test accuracy on a sample of 1. All right. So this is how you load the model. after you save the model, right? So you load the model, you save the model, and then you just load the model, you call the model X. After loading it in, and then you just do the argmax and say, okay, this is the class that it predicts to be, index number 9, and the ground truth is also number 9. And that's how you save and you load a model. So we covered a lot of grounds today in this video. We ran through a full complete example of creating a neural network and then training on the data, and then we got something like 80, what is the accuracy? Something close to 85, 86%, which is not bad at all. But this concludes the end of the quick start. And from this point on, this series is going to take a more intermediate step into showing you the different kind of applications of using PyTorch and actually building some really cool projects. But the foundational layers, I think I've covered all of the main concepts and the key ideas and given you sort of a bare bone neural network example. So with your newfound skills and you look forward to building more projects with PyTorch and building more hands-on deep learning examples, then subscribe to the channel and make sure that you check out the other videos on this channel as well. So I'll talk to you soon. See you. Bye.